A wave theory of light had been developed by Huygens and others in the 1600s. However, it wasn't until 1801 that an English scientist named Thomas Young performed a historic experiment that demonstrated the wave nature of light. His experiment was particularly important because he was able to determine the wavelength of the light from his measurements, which was the first such determination of this important property. The figure shows one arrangement of Young's experiment, in which light of a single wavelength, called monochromatic light, passes through a single narrow slit and falls on two closely spaced narrow slits S1 and S2. These two slits act as coherent sources of light waves that interfere constructively and destructively at different points on the screen to produce a pattern of alternating bright and dark fringes. The purpose of the single slit is to ensure that only light from one direction falls on the double slit. Without it, light coming from different points on the light source would strike the double slit from different directions and cause the pattern on the screen to be washed out. The slits S1 and S2 act as coherent sources of light waves because the light from each originates from the same primary source, namely the single slit. To understand why we see a bright and dark fringe at a particular point on the screen, we just have to examine the optical path length difference between each slit and that point. The geometry of the problem is shown in the following figure. Monochromatic light is shined onto a double slit with a slit separation distance d. Each one of the slits acts as a coherent source of light. We choose a random point P on the screen. Light from the slit S1 travels a distance L1 to point P, and light from the slit S2 travels a distance L2 to point P. The optical path length difference is just the difference L2 minus L1. If this difference is equal to an integer multiple of the wavelength, then the constructive interference condition is satisfied and we will see a bright fringe on the screen at point P. However, if the difference L2 minus L1 is equal to an odd integer multiple of 1/2 of the wavelength, then the destructive interference condition is satisfied and we will see a dark fringe on the screen at point P. In the figure, we see that the light from the second slit S2 travels an additional distance delta L to get to point P. Since the slit separation distance is small and the distance to the screen is large, the angles theta between the two paths L1 and L2 and the horizontal are essentially equal. From the figure, we see that the optical path length difference delta L is equal to d sine theta. Setting this equal to m lambda gives us the angles that satisfy the constructive interference condition, which correspond to bright fringe locations on the screen. Setting d sine theta equal to m plus 1/2 times lambda gives us the angles that satisfy the destructive interference condition, which correspond to dark fringe locations on the screen. M is known as the order of the interference. Let's see how the value of the order for the double slit is determined. The figure shows a typical interference pattern for the double slit. Notice we get a series of alternating bright and dark fringes, as well as a central bright fringe. The central bright fringe corresponds to the m equals 0 bright fringe. The interference pattern is also symmetrical about the horizontal dashed line between the slits and the screen. Thus, the first bright fringe both above and below the central bright fringe is the m equals 1 bright fringe. The second bright fringe, both above and below, is the m equals 2 bright fringe, and so on. In the figure here, the angle theta locates the m equals 2 bright fringe both above and below the central bright fringe. Since the central fringe is bright, the first dark fringe occurs directly above and below the central bright fringe. This is the m equals 0 dark fringe. The second dark fringe, located both above and below the central bright fringe, is the m equals 1 dark fringe, and so on. Remember that m equals the order, so if a problem tells you the order of the fringe, whether bright or dark, it's telling you the value of m. Historically, Young's experiment provided strong evidence that light has a wave-like character. If light behaved only as a stream of tiny particles, as others believed at the time, then the two slits would deliver the light energy into only two bright fringes located directly opposite the two slits on the screen. Instead, Young's experiment shows that the wave interference redistributes the energy from the two slits into many bright fringes at locations on the screen where the constructive interference condition is satisfied.